Hello everyone, today I am going to be doing my full review from chemistry of Thermochem. Now this is largely for my class, if anyone needed help. So let's get into it. First question. Number 1. Reactions that release energy would be considered either endothermic or exothermic. Well, they're releasing, so meaning they're getting rid of, or they're being external, therefore it is exothermic. Alright, in these type of reactions, is more energy needed to break the bonds in the reactants or released when new bonds form? Well, more energy is needed when, or rather released when the new bonds form, making it exothermic because of the properties of exothermic. So basically, positive net change of energy. I'm abbreviating because what I'm saying is the actual answers. In these reactions, is your overall net energy calculation a positive or negative value? Well, I just said it. Well, like, for example, I don't know, melting would be positive charge because the energy would need to be taken in. Yeah, basically that's it. Oh, well, I guess if they're taken in, then, sorry, I'm trying to think. Sorry. Let's just restart that. I skipped a question. I'm very sorry. In these types of reactions, is your overall net energy calculation a positive or negative value? It is negative because it's getting rid of. I'm very sorry. I skipped over 3. 4. Changes in state also release or absorb energy. Would melting have a positive or negative charge in enthalpy? Explain. Well, melting would be a positive change in energy because you need that energy to be taken in for the molecules to move faster or the temperature to change to go from different states, say to liquid to solid, because you need to actually put in energy to change that. So I'm not going to write that down. Alright, so for this, using the bond table, calculate the overall net energy of the following reactions. Indicate if the reaction is endothermic or exothermic. Alright, so we have basically just a data table of all these. So the equation to do this, let's say, is change in enthalpy, I can't pronounce it, I'm very sorry, of the reaction is equivalent to the energy used to make the bonds minus energy formed in making bonds. Now this sounds very complicated, but it's really not. It's basically just saying this is a negative sign. So, how can we just make sense of this? So we have a C and an H, or a carbon and a hydrogen bond in methane, and so we have 4 of these different bonds. Now let's find C and H. There it is. So it's 413 kilojoules per mole. We don't need to worry about our units right now. So we have 4 of these, so it's going to be 4 multiplied by 413, parentheses, plus 2 times, because we have 2 different bonds of these. It's also 2 molecules of that one. Either way works. So it's an O to O bond, which is a double bond, which is 495 joules per mole. Alright? I'm going to rewrite this over here, actually. Sorry. I keep on changing my mind. I haven't really done one of these things before. So 4 times 413 plus, parentheses, 2 times 495. We get 2,642. Subtract. So now we have to do this part. Sorry, this is notes I don't need right now. And so we have a bond from the O to the C and the C to O. So it's really just 2. So 2 multiplied whatever the double bond of C to O is, which is, it's a double bond. There it is. I was looking at that one. That is a 799. Alright, and then we're going to add plus, again, there's an OH and an OH bond, so that's 2 times 2. Now we're going to just do it this way because I'm kind of lazy. Of course you can combine it, but I'm not going to in this case. So what's the O to the H? Let's find that. Nope. There it is. 463. Alright, 2 times 463. Multiply that by 2 plus 2 times 799. Alright, I'm going to just put that in my calculator as x. And then 2,642, which is this number, subtracting this total. And the answer is not what I got. Yes, it is. I'm sorry. Again, negative 208 kilojoules per mole, which is the answer for this one. Alright, so let's do this one now. Now they say pay attention to the coefficients. Now they're really talking about these and these. And these, I guess. Alright, so, well, how many bonds does this have? Now, the important thing is we have 2 C to C bonds, and they are single bonds, so they need to be this. So it's 2, sorry. 2 times 348 plus how many C to H bonds we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 of the C to H, which is 413 again. Alright, now we're going to add the O to O, which is a double bond, but we have 5 of those, so we don't need to multiply that. And the O to O with the double bond is 495. Alright, and that is subtracting 3 times, so it's a O to C and then a C to O. These are double bonds, and that is this one, so 799 again. Okay, plus 4, because this is our coefficient, or a, how many moles of it do we have? Of course this is water, which is a 2OH, 1, 2. And that is, so 4 times 2 times OH, which is 463. I'm not going to bother putting this in my calculator. And you get a net change, not charge, I'm very sorry, of negative 2,023 kilojoules per mole. Alright, so this is where I run out of space, and that is why I have this guy. So, sorry, I'm repositioning here. Make sure it's still in here. So, another way that we can calculate energy absorbed or released in the lab is by using water. We use this process when calculating the energy in different food samples, as well as to determine the specific heat of an unknown metal. To calculate heat, or energy, we use the following formula. Interesting. Anyway, or the heat formula is Q, which is heat, Q is equivalent to change of temperature times S, or CP, which is what my chemistry teacher uses, and this is just specific heat times the mass. Alright, pretty simple. Alright, number 1. How much energy, or how much heat energy is absorbed by 100 grams of water when the temperature changes from 25 degrees Celsius to 30 degrees Celsius? Now, this just means that we have a net change of 5 degrees, so Q is equivalent to 5 multiplied by 100 grams, and this is liquid water because of the temperature range, and the specific heat of water, liquid water, I'm sorry, is 4.182. Yes, 4. Sorry, I had to check that. And we just solve. So we get 5 times 100 times 4.184, which is 2,000. So for this first one, it's going to be 2,092 joules, which is basically 2 kilojoules. Alright, pretty simple. Interestingly, this goes to just 3. Whatever, doesn't matter. Alright, let's put a line through here. And number 3 is, what mass of water is used when 5,000 joules are added and the temperature changes from 40 to 50 degrees Celsius? Same equation, different way to solve. So we're going to do 5,000 on one side, and our change is 10, and it is still liquid water, so we still have that. And we're multiplying that by x. That's what our variable is. So x multiplied by 41.84 is equivalent to 5,000. Basically, basic algebra. By 5,000, we find that x is equivalent to 119.5 grams. And I'm just putting it in whatever order. It's bad, but as long as it works, that's all that matters, really. Yeah, so that's for this side. Time to do the other side. Sorry if you can't see it all that well. I need to put this in here. Sorry. Again, keep on saying sorry. What is the final temperature of a 50-gram sample of water? So that's one of our variables. Initially at 20 degrees. And it releases 2,000 calories. Now, that is not kilocalories because it's a lowercase c. So, we need to convert calories to joules, which, by the way, is the specific heat of water. So that means that 2,000, so we're just going to convert by, 1 second, I need to check something. Check that my math is right on this, so I'm not going to do this on camera, because I don't like to be wrong. Okay, so 2,000 joules, 2,000 calories, sorry. Multiply that by, I can't think, 4.184, because that's just our coefficient change. Yep, so we have, sorry, that's not a very good explanation. What can I think about this? For 1 cal, there's 4.184 joules. Okay? That's pretty easy. That's our conversion factor. I didn't write that before, sorry. So that's how many joules we have. And that's one side. Initially at 20, we're looking for final change. So we're looking for change. We have 50 grams. Multiply that by x. That will be solving for our change. And we know our specific heat again is 1.84. Okay? Pretty simple. Just do some basic algebra again. I'm gonna not do this on paper because I'm just gonna save some time. Yep. 8373.6, and you get 40 degrees change. Now you take your 20, and it releases. Therefore, you should take this, take it away, because you're releasing. You're getting rid of energy. So you're making it actually colder, and therefore it should be at negative 20 degrees Celsius at the end. Okay? Pretty simple. Okay, number 5. An almond was buried under a 25 milliliter sample of water. Burned. Oh, I can't read. I'm very sorry. I hope you can't read. Anyway, an almond was burned in a 25 milliliter sample of water. The temperature changed from 23 degrees Celsius to 27 degrees Celsius. How much energy was in the almond? Okay. Pretty easy. We're just solving for joules again. So, in real life, your percent error will be bad. Really bad. But our first thing we need to do is convert this 25 milliliters. So we just do 25 times 1,000. I mean, divided by 1,000. Sorry. And you get, so our milliliters is 0.025. Now this is water, so it's really just grams. And it's close enough. At standard pressure anyway. Okay? And the temperature change was 4 degrees, I think. Yes. And our specific heat of water. Oh, specific heat of water is 1 cal. So we've changed our units to for specific heat. So when we solve, we'll actually just find the calories, which is kind of nice. So we actually get to skip that step essentially. And then we just do some basic math. So 0.025. Multiply that by 4. Multiply that by 1. And you get 0.1 calories. I did something wrong. 1 calorie per gram. I realized I made an amazingly dumb mistake. 25 mils, that's 25 grams. Meaning I was off by quite a lot. So this should be 100 calories. Sorry about that. Wasted a bunch of time. Sorry, again. Okay. A sample of aluminium with a specific heat of 0.90 joules per gram per degree Celsius was heated to 75 degrees Celsius and placed in 100 milliliters of water at 22 degrees. The water's temperature increased to 28 degrees. What was the mass of the metal? Okay, pretty simple. So this is when you have to deal with this equation. Q lost equals Q gained. Okay, so we have a bunch of different things. Bunch of different measurements. And so the equation we're going to be using is basically the same. So mass times change of temperature, multiply that by the S is equivalent to mass 2 times change of temperature 2 times the specific heat 2. Now these are not squared, they're just different things. Okay, so aluminium has a specific heat of 0.90, was heated to 75 degrees, and the final temperature was 28 degrees. So 75 minus 28 is 47. 47 was our change. Okay? And we're looking for mass, and so that's our unknown. And so the rest of this is super simple. It's 4.184 multiplied by that by 100, because it's 100 milliliters. And it changed by 6 degrees. Okay? And again, I'm not going to put this in because it's so easy. I can even make mistakes, so it's 59.3 grams. Pretty simple. Alright, now we get to do change in enthalpy, or delta H, in a chemical reaction using Hess's law. I've already made a video on this, so it's pretty easy. Alright, time to go back. Okay, how much heat will be released when 25.7 grams of hydrogen reacts with an excess of oxygen to create water? Alright, well, we're talking about hydrogen gas. So we're going to divide this 25.7 by 2, because it's H2. So we get 12.85. Alright, now we want to multiply this by negative 571.6. I just put that in my calculator. That's not how you do math. Alright, and then we divide this by 2 because we have 2 moles of it. And so we found it per mole. And we just need to divide it, and we get our answer of negative 3,672.5 joules. Alright, for the second one I decided I'm going to do a little bit of a different strategy. Now, I'm not actually sure if this always works, but I'm kind of lazy. So, I know it works, so whatever. It might not work for any other equation, but it does work for this. So, 50 grams of bromine react with an excess of hydrogen in the following equation. H2 plus Br is equivalent to 2HBr. Now, I think it's because of this, actually. But whatever. I'm still going to go through it. So I'm not actually sure of any other way. So, bromine here has a 79.9. Now, you multiply it by 2. So you have Br2, so 159.8, I believe. I'm going to divide that by 50. For the other one, I did it the opposite way. But for some reason in this equation it works, so I'm going to do it that way. Because I can. Okay, we get that. Now we divide it by 2. And then we multiply it by 72.80. That's not what I wanted. One second. It needs to be divided. Again, I'm so sorry. I'm making stupid mistakes now. 1.58. And I got 46. Is that right? No. Well, it's close enough. 46 joules. Kilojoules, actually. Alright. Hess's law, super simple now. Actual Hess's law, that's super simple. Alright, so we got this. It's the exact same as this, it's nowhere else. And it's on the opposite side, we're going to flip this. Okay. And on here, what do we have? Looks like we have the sulfur trioxide. So that's it. It's the same ratio, so we're going to keep it the same. And the H2 is gas. So we're going to add this as well. So it's going to be 44 plus negative 207 plus 235.5. And we get 72.5 kilojoules. Is our final answer. Okay, for this one, it's pretty simple again. CH2O is here, right? Yes, it's in gaseous form as well, but we need a flip. And more importantly, it also gets this on the other side as well. NH4, this needs to be flipped. These are on the right coefficients. Right coefficient 3H2, correct. And yeah, so we already dealt with that, already dealt with that. H2, same, okay. And we just add these together. This also becomes negative, negative, and we get, let's see, so negative 22.5 plus 57.5 plus negative 81.2, which is negative 46.2 kilojoules. Alright, this has been the review. Sorry about the jump cuts and the bad camera that I just noticed. This was largely for myself, just to see if I could even try and explain it. I know how to do it, it's just I don't know how to do it on camera. Alright, thank you for watching. Have a nice day.